Hello everyone, thank you for coming today. My name is Peixin Zhang, a PhD candidate from Zhejiang University. I'm glad to be here to present our paper, White Box Fairness Testing through Adversary Sampling. The reason why we study fairness is that in modern society, discriminations such as racism and sexism are still common to see and even become more intense nowadays, which leads to there are often societal bias in the collected data. Thus, deep learning models learned from historical data might introduce discrimination unintentionally. Then, with the spread of deep neural network, its fairness raises more attention among public, especially the minority. Therefore, governments, including US, Chinese, and European Commission, all list fairness as one of the most important principles for trustworthy AI in their AI development guidelines. Actually, there are multiple definitions of fairness in AI and the software engineering community, such as demographic parity and equal opportunity. In this work, we only focus on solving the problem of individual fairness, which is defined as a model must predict the same labels for all feature factors that are the same except for those protected attributes, such as gender and race. And we mark those valid instances which violated the given definition as individual discriminatory instance. For example, for a toxic classifier, it should give the same predictions on the given examples where gender is the protected attribute. Now, the problem of fairness testing is how can we effectively and efficiently generate individual discriminatory instances for a given model. There are three existing individual fairness testing methods. They either relies on the randomness or combines model explanation and symbolic execution, which limit their effectiveness or efficiency. Besides, although they are suitable for all the machine learning algorithms, they perform much worse in deep learning models according to their experiment. Therefore, we try to design a better algorithm specifically for deep learning models. According to the definition, individual fairness can be seen as a specific form of robustness, which maintains the prediction when protected attributes changed. Thus, inspired by the adversary attack, we try to perturb X and X apostrophe which only differ on the protected attributes at the same time to push them towards the decision boundary. And if only one of them across the decision boundary, we are successfully obtain the individual discriminatory instance. Here is the overview of our algorithm ADF. We divide it into two stages. First, global generation aims to increase the diversity in the generated individual discriminatory instance. And then, based on the robustness of deep neural network, local generation tries to obtain more and more individual discriminatory instances by searching the neighbors on the identified ones. Although both phrases need to calculate the gradient, they utilize it in a different way. Next, we will detail these two phrases. In global generation, there are three challenges needed to address. The first one is how to improve the diversity of the testing data. We provide a direct way by clustering the data and popping the seed in a round-robin fashion. And second, how do we perturb the data? Inspired by fast gradient sign method in adversary attack, we select the perturbed attributes with the same sign of gradients and utilize the sign as perturbation direction. And last, how do we keep the generated test case real? Since the experimented datasets are quite simple, we only clip each attribute within its domain. Compared with global generation, Local generation is much easier. Its first problem is how do we choose the attribute to perturb. Since gradient shows the impact on output, we select the perturbed attribute based on the absolute value of gradients. And the same with global generation, we clip each attribute within its domain to make data valid. Compared to existing approaches, our algorithm satisfies all the listed three criteria. First, ADF is guided by gradient, which accelerates the discovery of more individual discriminatory instances. Second, our algorithm is input specific, which improves the diversity of generated test cases. Last, ADF is lightweight, which makes it more scalable. We evaluate ADF with 6 benchmarks on 3 popular tabular datasets. Since the datasets are quite simple with no more than 20 features, we only use a 6-layer fully connected neural network, and we aim to answer 3 research questions about the effectiveness and efficiency of ADF, and the usefulness of individual discriminatory instances identified by ADF. First, we conduct effectiveness evaluation phrase by phrase for a fair comparison. Both in global and local generation, we try to generate 1,000 test cases and check whether they are individual discriminatory instances. It is evident that our algorithm ADF is more effective than state-of-the-art methods. Next, the table lists the time each method takes to successfully generate 1,000 individual discriminatory instances. It is clear that our algorithm ADF is more efficient. Last, we try to improve model fairness by retraining with data augmentation. The table gives the ratio of individual discriminatory instances estimated by the law of large number. It can be observed that retraining with the individual discriminatory instance can significantly improve the model fairness, and ADF achieves better fairness improvement. In conclusion, inspired by adversarial sampling, we propose a lightweight algorithm to effectively and efficiently generate individual discriminatory instances, and in the future, we try to expand it to text and image domain. This is the end of my presentation. Thank you very much for your listening.